Alright everybody, welcome back. In this video we're going to start working our way through the chain rule part 3 lesson in support of Unit 3 Section 1 of AP Calculus. We've had a few other videos for the chain rule part 1 and chain rule part 2 that are available. In this video we're going to focus on taking the derivative of composite functions where it's a multi-composite, not just a composite of two functions, but a composite of three or more functions. And how we're going to deal with this situation. And that's probably going to be it for this video, and then we'll probably have a second video from this lesson where we do some numerical problems and practice some general derivative rules and numerical problems and revisit that topic. Only incorporating the chain rule this time. Alright, so let's get down to business with this video. We're going to start with example 1. Find dy dx if y equals cosine squared of the quantity 7x plus 2. Now you want to make sure that you're thinking about this, even if you don't rewrite it this way, but you should always be thinking, whenever you have like a trig function raised to a power here, you always need to be thinking that this is the quantity cosine of 7x plus 2, that whole quantity raised to the second power. Okay, and so now what we really have here is we have three functions in composition. We have the very inside function, which is 7x plus 2, and then we have a middle function, the cosine, and then our outermost function, raising something to the second power. And when we have multiple composites like this, what we're going to do is we're going to start with the outermost function and work our way to the inside, continuing until we've taken the derivative of the innermost of the composite functions. So once we've taken the derivative of 7x plus 2, we're done taking the derivative in this particular problem. Alright, so let's go ahead and get started. Dy dx, we're going to take the derivative of the outside, leaving the inside the same. And in this context, we're talking about 2 as our outside, and our inside is the cosine of the quantity 7x plus 2. So the derivative of the outside, leaving the inside the same, times the derivative of the inside. And now we're going to continue on. And we still have this 2 cosine of 7x plus 2. I'm going to get rid of the brackets and the raised to the first power. And then we're going to multiply that times the derivative of cosine of 7x plus 2, which again we need to apply the chain rule here. Derivative of the outside, in this case the cosine is the outside function and 7x plus 2 is the inside. So derivative of the outside, leaving the inside the same, times the derivative of the inside. And I don't want to write a whole other line to take the derivative of 7x plus 2. That derivative is just 7. And then I'm going to sort this and organize it, and I want to bring my negative sign and all of my constants out to the front and combine them, since this is all a multiplication of all these things. So we end up with negative 14 cosine of the quantity 7x plus 2, sine of the quantity 7x plus 2. And there we are. Okay. Alright, let's look at example 2. We're going to find dy dx if y is equal to the sine of the quantity 3x squared plus 2x raised to the third. Now notice in the last one, the exponent was the outermost function, but in this one, the sine function is the outermost function. This is not equal to the sine of the quantity 3x squared plus 2x all raised to the third. That's different from what we're seeing here. So we've got three functions here. We've got the outermost, which is the sine function. We've got the middle, which is the exponent. And we've got the innermost, which is the polynomial. So we're going to work on the outside and work our way in. So we take the derivative of the outside, leaving the inside the same. Derivative of sine is cosine. Leave the inside the same, times the derivative of the inside. and then we leave that cosine of the quantity alone. Now we're going to take this derivative of the outside, leaving the inside the same. Now the outside is that exponent, so it's going to be 3 times the quantity to the second times the derivative of the inside. The derivative of the inside of this is 6x plus 2. Okay, now we're done with all the calculus. All we have left is a little bit of algebra, and what we'd like to do here is we would like to go ahead and, factor out our constants and write this in the least ambiguous way possible, which means I'm going to push this trig function all the way to the end when I write this. So let's see, I'm going to factor a 2 out of this, which gives me 6 times the quantity 3x plus 1 times the quantity 3x squared plus 2x, quantity squared, times the cosine of the quantity 3x squared plus 2x, all to the third. And that's going to be our final answer. Okay? All right. And one last example we'll go for in this video. Example 3, find dy dx if y equals the quantity tangent of the secant of the quantity x squared plus 5 quantity squared plus 3 raised to the 4th power. Whew. Have you ever, well, you guys don't really write lessons, so I was going to say, have you ever written a problem and as soon as it's time for you to do it, immediately regretted the problem that you've written? I'm having one of those moments right now. This is going to be complex because we are going to apply the chain rule, probably 4 or 5 times here. So we need to start with the outermost and work our way in. And so we're going to go ahead and do that. It's just, more steps and more complicated. So the outermost function is raising to the 4th power. So it's going to be 4 times the tangent of the secant of x squared plus 5 quantity squared plus 3 all to the 3rd power. That's the derivative of the outside, leaving the inside the same, times the derivative of the inside. And now the inside here is actually a sum of 2 things. It's the sum of tangent of that whole quantity plus 3. When we take the derivative of that plus 3, that's just going to be 0. So in essence, when I take this derivative, all I need to take the derivative of is that tangent of the secant of etc. So I'm going to leave this first part alone. Till I get done with this problem, I'm going to have recopied this statement a number of times. And now I'm going to take the derivative of the green highlighted portion, tangent of the quantity secant of x squared plus 5 quantity squared. So I'm going to use the chain rule here. Derivative of the outside, derivative of tangent is secant squared, leaving the inside the same, times the derivative of the inside. And now I need to bring all this other stuff down. So much to write. Now I'm going to take the derivative of the quantity secant of the quantity x squared plus 5 quantity squared. That's going to be derivative of the outside, the secant, leaving the inside the same. Derivative of secant of a quantity is secant of that quantity, tangent of that quantity. So the derivative of the outside, leaving the inside the same, is going to look like this. Secant of x squared plus 5 squared, tangent of x squared plus 5 squared. And then I need to multiply that by the derivative of the inside, which is the derivative of x squared plus 5 quantity squared. Okay, almost there. So we've got all this stuff still. My goodness. Now you see what I mean about regretting this problem as soon as I wrote it. And now I'm going to take the derivative of the outside, leaving the inside the same. The derivative of the outside is the exponent, so this is going to be 2 times the quantity x squared plus 5 to the first, times the derivative of the inside, and I'm not going to rewrite a whole line to take the derivative of x squared plus 5. That derivative is just 2x. And now I want to clean this up as much as I possibly can. So what I'm going to do is I'm going to combine all my constants and my x out in front and set myself up for my final answer. So that's going to be 4 times 2 times 2x is going to be 16x times the quantity x squared plus 5. So that takes care of all that stuff. And then everything else, the order in which I write it really isn't going to change whether it's ambiguous or not. So I'm just going to go ahead and copy it down in the order that it appears. And there we go. This is going to be our derivative of that original monster of a function. And the derivative is even more of a monster. Alright, that's it for today. So now you've seen from this video what happens when we have a multi-layered composite function. We just work our way, start on the outside and work our way in, continuing to apply the chain rule until we've gotten to the point where we've taken the derivative of the very last inside, and then we simplify things algebraically, and we're done. Alright, we're going to call it quits for that for today's video. Next time we'll come back with some numeric examples, and hope to see you then. Have a great rest of your day, everybody, and enjoy yourselves.